Now we will study the concept of tangent space. As tangent vector is defined at a point P, which is called point of application, and is directed towards the point P plus V. Now, what actually tangent space is? The definition is, it says that let P be a point of E3, as we are studying everything in the Euclidean 3 space. The set Tp of E3 consisting of all tangent vectors that have P as point of application is called tangent space of E3 at the point P. So suppose this is a Euclidean 3 space with x, y, z are 3 coordinates. Suppose this is the point P, then UP can be one tangent vector, VP, WP. So in different directions we are having different tangent vectors. Therefore, by collecting all the tangent vectors at a particular point of application, that form a space that is called as tangent space. And we are studying E3, therefore that is called tangent space of E3 at the point of application P. So have a note. So E3 has different tangent space. Different tangent space at each and every one of its points. So to know about operations on tangent vectors, since all the tangent vectors in a given tangent space have the same point of application, therefore we can define vector addition and scalar multiplication operations. On the tangent space Tp of E3, so which is same as in the vectors in E3. So suppose Vp and Wp are the tangent vectors in Tp of E3, then the sum of these two, Vp plus Wp, is equal to P plus Wp at the point. For this holds for any tangent vectors Vp and Wp in Tp of E3. So similarly, this is called a vector addition. The sum of two tangent vectors is again a tangent vector. Scalar multiplication, if suppose alpha belongs to R, is a scalar, which is any scalar, and Vp is any tangent vector in Tp of E3, then the scalar multiplication of alpha to Vp is equal to alpha v of p. So this holds for any tangent vector Vp belongs to dp of V3. Therefore, both the operations of vector addition and scalar multiplication holds in dp of V3. Hence, by two-step test of vector space, test for vector space, dp of V3 is a vector space. So here we have a remark about the operations of vector addition and scalar multiplication. What it says here, the vector addition in dp of V3 is nothing but the usual parallelogram law of addition. As we have two vectors, and for addition of two vectors we will follow the parallelogram law of vector addition. So, and what will the operation of scalar multiplication do? Scalar multiplication by alpha means it either stretches tangent vector by a factor alpha, or sometimes it may decrease its length. Or it may reverse the direction of the vector. Based on the sign of, which is based on the sign of alpha. So this is about the operations of vector addition and scalar multiplication on the tangent vectors. So here if we add two tangent vectors, then that will be a tangent vector which is obtained with the help of parallelogram law of vector addition. And scalar multiplication means it will either stretch the tangent vector, or it will decrease its length, or sometimes it will changes its direction. So these things can happen in case of the operations of vector addition and scalar multiplication. So earlier we have said dp of V3 is a vector space. So now it is time to know what is the dimension of the vector space, because if we know about the vector space, then we will think of what is the dimension of the vector space. Now, so thinking about to know about the dimension of dp of V3. So in order to know the dimension of dp of V3, it is better to show dp of V3 is isomorphic to some known vector space, so that we can directly tell the dimension of dp of V3. So our aim is to show dp of V3 is isomorphic to the usual three-dimensional Euclidean space E3. So because we know the dimension of E3, for that we have to show, so we have to define a function from E3 to dp of E3, and we have to show the function is 1 1 onto and homomorphism, means the function is isomorphism. So then only we can directly say that the dimension of TP of E3 is same as the dimension of E3. So first let's show. So 1 1s for 1 1s. So define a function pi from E3 to TP of E3 by pi of V is equal to Vp for all E belongs to E3 and Vp belongs to TP of E3. Means for V belongs to E3, P3 belongs to TP of E3. Now consider pi of V is equal to pi of W. So then this is possible only when Vp is equal to Wp. So this implies V is equal to W. So this, if it is possible, then the function is 1 1. So before that we have to know whether the function is well defined or not. Therefore we have to go in the reverse direction. Suppose V is equal to W, means two vector parts are same, then they will be equal only one. They have same point of application. We can come reversely. Therefore V is equal to W means Vp is equal to Wp. By the definition of pi, Vp can be written as pi of Vp is equal to pi of V and Wp is equal to pi of W. So in both directions it will follows. Therefore the function pi is both well defined and 1 1. Now moving on to the onto property. Since for all Vp belongs to TP of E3, there exists V belongs to E3, because for every tangent vector there is a one vector part. Therefore for all Vp belongs to TP of E3, there exists V belongs to E3 such that pi of V is equal to Vp. This says that pi is onto. So next what we are left with is, we have to show the function is homomorphism. To show pi is pi from E3 to TP of E3 is homomorphism. So for showing homomorphism we have to use both operations of vector addition and scalar multiplication. Now consider pi of V plus W. This is vector addition. This is equal to V plus W of P by the definition of pi. So the addition of two vectors is equal to the tangent vector. This is equal to pi of V and plus pi of W. So this holds for vector addition. Similarly consider pi of alpha of V. This is equal to alpha V of P. Since alpha is a scalar, we can take it out. So this is Vp. This is equal to alpha into pi of V. So both vector addition and scalar multiplication follows the properties of homomorphism. Hence pi is homomorphism. Therefore from the results 1, 2 and 3, phi is an isomorphism. So this implies TP of E3 is isomorphic to E3. But we know that dimension of E3 is equal to 3. So this implies dimension of TP of E3 is also equal to 3. So this is how we can find the dimension of TP of E3, which is based on the known vector space E3 whose dimension was 3. So this is about the tangent vector space and its dimension.